It's just over 20 degrees centigrade this January 20th, 2011 in my basement laboratory, where we have a 90 centimeter standing wave tube connected to a single low frequency driver here, and that's driven by an amplifier controlled by a sine wave generator. We have a power meter here, frequency counter here, which I'll set down to around 50 cycles per second, and in between is a Venturi meter, a plastic tube filled with colored water, and we have a ruler glued to the side of that. Now, as I set this down, what we're going to do is, in a manner of the Pitot tube, we'll take the tube that's labeled T, and that tube we're going to connect to an end cap of the standing wave tube, and we're going to put that in so that it measures the transverse pressure inside the standing wave tube, and the other tube, the one corresponding to L, will measure pressure along the long axis, and we'll see the difference in the longitudinal and transverse pressures as they're simultaneously measured in this with the Venturi pressure meter. Now, I've put the end cap on at the node here. That's where we'll be doing the pressure, and as you watch, I will increase the amplitude over here to about 3 watts, just up to this level. Okay, that's 3 watts. There's been no change in levels here yet. At 48 cycles per second, I'll increase the frequency up to 100. Our expected resonance is at 90 for a 95 centimeter standing wave tube. We're beginning to see a change in level. Now it's about a ½ centimeter difference. And we're peaking right around 90 cycles per second. If I continue, we lose that by about 108 cycles per second. We've lost that peak. If we come back down, right there we seem to have it again, and if I turn down the amplitude, we lose that pressure difference. If I increase it again, this is a ½ watt, 1 watt, 2.5 watts, 5 watts, 10 watts, and then back down to 0. So the difference in long axis and transverse axis pressure at a node and a standing wave is real. It's readily measurable, and I believe useful work can be extracted from it.